It is my pleasure to introduce Ciprian Corneanu. So he's currently the head of the research at Tony, which is a Munich-based startup developing emotional AI solutions for the consumer market. He was previously a research assistant at the University of Barcelona, where he also obtained his PhD, and a fellow of the Computer Vision Center also in Barcelona. His research interests include face and behavior analysis with deep learning, affective computing, social signal processing, and human-computer interaction. But today he will present his CVPR 2020 work on the topology of deep networks that generalize. And this was the Best Paper Award nominee at CVPR. So we're definitely looking forward to your talk. And the floor is yours.
Thanks, Laura. Yeah, thank you so much for giving me the opportunity to present to you this this work, which is about deep learning and about algebraic topology and how using algebraic topology can shed a new light in what deep neural networks are doing. So Laura already presented me, so I'm not going to insist on that. I'm just going to tell you briefly a few words about what we are trying to do in Tony. In Tony, we are trying to provide emotional AI solutions for the marketplace. And I'm kind of like trying to direct the research efforts in deep learning and facial analysis there. And we're mainly focusing on emotion analytics for market and media research, for user experience and digital testing. And we also have collaborations with different universities, especially in the economics department, for consumer behavior research. So before beginning, this has been a work, what I'm going to present to you today has been a work done in collaboration with Sergio and Meisam from the Computer Vision Center in Barcelona and the University of Barcelona, and with Aleix Martinez from the Ohio State University in the United States. And it has actually been published in 2 CVPRs, the one this year that Laura mentioned, and the previous one the year before. And it makes sense to like present them together because it's mainly the same corpus of work. They're basically deriving from each other. So let me give you a short overview of what is this all about. Now, deep nets, as you all are very well aware, in these recent years have achieved amazing boost in performance in a myriad of tasks in machine learning, be it object recognition, semantic segmentation, image captioning, text translation, and so many others. Unfortunately, this has come at a cost, and we have landed up in a quite weird situation in which we have models that are quite easy to use and flexible. We have this boost in performance, and we design the architecture and the optimization process itself, but at the end of the day, we don't know exactly what the deep net does. So deep nets are regarded more and more as black box models, and we don't know exactly when are they learning, how are they learning, when will they fail, and by how much. So we are trying to shed a little bit of light on these questions. When you're going to have an image and you pass it to a deep net, then you're going to have a prediction, but what does the deep net do, right? So there's like a question mark here. This is our focus today. What is happening inside the deep net? And my promise to you today is kind of like the following. So we're going to take a deep net, and through a set of steps that I'm going to present to you in short, we're going to study its functional topology. And by looking at its functional topology, we're going to try to answer a set of questions, mainly if the net has learned, if it will generalize, and how well is it going to generalize. And I'm going to present to you two main findings. One is that functional topology of networks that generalize differs fundamentally from, those that simply memorize training samples. And this has been mainly the focus of CVPR 2019. And then the main set of findings focuses on the fact that given a domain and an architecture, descriptors of functional topology correlate with the generalization gap. And this is the CVPR 2020. And based on these two main findings, we can discuss a set of applications, mainly in early stopping, in detecting adversarial attacks, and improving training of deep nets. All right, so let me tell you a few words of how we're going to approach this. Now, a deep neural network is nothing else than a parameterized functional mapping between a set of inputs, X, and some set of desired outputs, Y. And in the case of deep network, this functional mapping F is usually a composition of a set of simpler subfunctions that I denote here by F1, F2, Fn. So when you're going to take an input and you pass it through this network, each one of the more simpler subfunctions will produce an output. And these outputs taken together are a representation of that input space X. And what we are trying to do, we are trying to study topologically how this representation looks like. What is the quality of this representation? And when we are talking about learning representations, there are two main opposite ways in which you can learn a functional mapping from an input X to an output domain Y. And we name this memorizing and learning. And when we talk about memorizing, I'm usually talking about a representation that is more sample dependent. So this type of representation focuses in capturing idiosyncratic variations in the input domain. And we know that this is totally possible because this has been shown a few years ago that even if you take a random set of inputs and you associate to it some random labels, a deep net has the capacity to perfectly learn this random association without problem. And in this specific case, even though you would have maybe almost perfect training accuracy, the model is not going to generalize well to unseen samples, which you can measure by a high generalization gap. On the other hand, if you're learning from data, then the representation is less sample dependent. And you're going to have a distributed representation in which parameters across the network computationally contribute to many different samples. And this type of representation will generalize well to unseen samples, and this will be measured by a low generalization gap. So I tried to put together a kind of like a very silly example, just to try to visualize a little bit this. So imagine you have some input domain, let it be faces, let's say. And imagine that you can walk that input domain. So you have a set of faces, and in this case, for example, is some blending between some guy and this lady, right? And as you walk through this input domain, you pass it, each sample, each step, you pass it through the network. And then let's say that you are able to collect, to register, to record all the representations here, all the outputs of the subfunctions that you have in the network. And in some sort of way, you could map this to some kind of a circle, color circle, right? And in the case of memorizing, then each one of these samples will map to very different colors. The representations will be quite different. They will be very sample dependent. Right? Now, on the other hand, if you are learning from data, this type of what the network produces is way more structured, and it will have certain type of properties. So it will probably have a smoothness property, it will be expressive, it will be distributed, and it might, in some cases, have factorize different express different factors of variations in the input as well. So what we are trying to study is there a way of compactly describing the difference between these two situations? Is there some kind of way of putting a compact expressive descriptor on the way this deep network reacts to input, to some input? And a very nice approach to this is if you would be able to study the representation topologically. And this is the focus of this corpus of works. So what we're trying to do is to take this functional mapping and project it into a topological space. So how do you do that? Well, first of all, we have a deep network. Let's say we have a deep network that is already trained, and you have a set of inputs, and you pass the set of inputs to the deep net, and you record the outputs of each of these sub-functions, each of the nodes in the network. And each of this is going to constitute a random variable. And based on this, we define a metric space. And in this metric space, each one of the points here, they're going to be a node in the network. And the distance between them is going to be the inverse of the correlation to input. So the closer these points are, more correlated different nodes in the network, the responses of different nodes in the network are to input. So now we have a set of points and an associated metric, which is this correlation. And what you can do with this, you can transform this into a set of topological objects. And there is a way, I'm going to show you immediately, to put compact descriptors on invariant properties of these topological objects.
One question, please. Can I ask questions? Or later?
If you want, yeah. Maybe you could keep the question and I'll answer them at the end. Okay. Yeah.
Yeah, it was more about understanding again. I didn't get 100% like the metric that you were introducing. So
all right.
Just
okay.
So quickly, maybe if you could maybe explain this once again.
So you have this deep net, right? And this deep net is going to be composed of a set of nodes, and each node has an associated sub-function, right? As I showed like in the beginning. So now you take a set of inputs and you pass it through the network and you record the output of each of these nodes. And what you do, you compute the correlations between these outputs. And by this, you can define a metric space where each of these points is a node in the network. And the distance between them is going to be the inverse of this correlation. More correlated they are, closer they're going to be in this metric space. Does this make sense?
Yes. And the correlation is basically all activations are a vector and another activations are a vector, and then it's kind of like a correlation between these two vectors.
They are two random variables, actually. Okay. As you pass input, you're going to create a set of random variables and you can compute the correlation. You take its absolute value. It's going to be between 0 and 1, which you can treat as a metric, and you build this metric space. Right? You have a hypersphere if you want, and you will have all these like nodes in the hypersphere. And now from the metric space, so in the metric space you have a set and a metric, right? In topology you have a set and a connectivity. And there is a very well established way in algebraic topology from passing from a metric to a connectivity. And this is done through a process which is called filtration. And what you are doing is you're gonna vary a distance, which I denote here by epsilon, in a range, let's say from 0 to some maximum range to the max of that range. And as you increase this distance, right, that you see here with this increased size of these circles, you're going to define a connectivity in such a way that each 2 points that are closer than twice this epsilon, they will be connected. So now, in this range of epsilons, we create a set of topological objects, which are called simplicial complexes in algebraic topology. And there are tools in algebraic topology that allow you algebraically to compute invariant properties of these topological objects. And one of the most interesting invariant properties are cavities. So you might notice that as you increase this type of distance, at a certain point you start forming cavities. And if you keep increasing this epsilon, you will fill these cavities. And persistent homology in algebraic topology will tell you when exactly at what epsilon this gets created and at what epsilon this gets filled. It's basically what I'm like showing here. So from this metric space, through filtration, you get a set of topological objects. There are tools in algebraic topology that will give you the pairs for each cavity. When is it formed? When does it die? And now, based on these pairs, we define an average life of these cavities, which is basically how much do they live through the filtration, and an average life of these cavities, which is basically around what distances are they formed in the metric space. And another descriptor, which is a little bit more comprehensive, is what is called a Betti curve, which will basically tell you, will give you a function like this, that will give you the number of cavities for all the distances in the range that you have considered. So this will be a vector, let's say. So to recap, you have a deep net, an input domain, you sample that input domain, you pass it through the network, you build a metric space. This metric space, you can project it into a topological space. Through a filtration, you can create a nested sequence of topological objects. And by using algebraic topology, you compute persistent cavities of these topological objects. And based on that, you get a Betti curve and the average life and midlife of the topological objects. So now from a deep network, we are having, if you like to see like this, a kind of geometrical object, which will have some sort of very weird, complicated shape, right, in a high dimensional space. And we can resume this to basically a set of numbers. All right. So what is actually happening, right? So I'm going to show you a set of things that we tried and that we think are very interesting. So the first thing that we just tried to do was, all right, how does the topology of a network change when I am training that network? So let's say you have, in this particular case, this is LeNet, a very simple toy network trained on MNIST. And from left to right, each column corresponds to an epoch in the training from 0 to 50. And this more or less, just to have like a reference, will correspond to a training accuracy that looks like this. So from random to basically almost perfect match. And each one of the rows is the Betty curve in 2D, in 3D, and in 4D. I don't know if I mentioned, but you can actually compute these topological descriptors in different dimensions. So as you train this deep neural network, some interesting shift in the Betty curve occurs. And mainly, so what you have here is the inverse of that epsilon of the distance on the horizontal axis. And as you train the network, more and more cavities in all these dimensions start forming at lower and lower distances. And this is quite interesting. So like, why is this happening? So there must be some kind of structuring of that metric space that represents the deep neural network that is illustrated in this shift of these Betty curves, right? And another interesting thing is like what we observe is there are actually two phases in this dynamic that basically at until a certain point in the first phase, you have formation of these cavities and at these lower distances. And in a second phase, the actual maximum peak here starts shifting to the left, which means that you more or less preserve or create more cavities, but they start forming at higher and higher distances in the second phase of training. And usually this corresponds exactly to the phase that is here from, let's say, epoch 2030, this part of the phase where the accuracy in training is plateauing, is flattening. So why is that? So I'm just trying to give a slight interpretation of what might happen. In the beginning, that metric space is unstructured. The network is random, right? So you won't have any kind of particular pattern here. And thus you're not going to have any kind of cavity. Now, as you start training and training and training, then you start structuring this space, and you start forming these cavities. And this curve just gets more and more accentuated. But if you keep training, then what the network is doing is that it's going to be on that plateauing side of the accuracy, and it's going to try to focus more and more on more specific samples that it couldn't get in the first phase. So it's going to basically try to memorize that to get that last 1, 2, 3% in the accuracy. And while it's doing that, it will create the same level of cavities or more, but it will do that by memorizing specific samples. And you'll see through this shift here towards higher distances of the curve. So the second thing that we try to do is like, okay, this is how the dynamic of the network looks like during training. What if we do a slightly different thing? So consider the two options. Option number one is what I showed you before, normal training, which is illustrated here in blue, and which will basically mean that accuracy in training and testing will both go up more or less in the same time with a certain kind of gap. Maybe towards the end, this gap will slightly increase. Option number two, we take our inputs and we do a shuffling of the labels, and we keep this shuffling constant through the training. So now each sample will have some random label. But because this label is constant through training, the network is going to be able to match that. But the only way to learn to improve accuracy in training will be by learning this specific idiosyncratic association between a particular input and some random label. And this will result in the accuracy in training going up, but the accuracy in testing basically staying random, right? So this will be the curve here in orange, right? So again, each column, they're going to be different epochs as you train more and more. Betty in 2D, the cavities in 2D, cavities in 3D, cavities in 4D. When you train normally, you form the cavities at lower distances, as shown in the blue curves. When you memorize the samples, you don't form these cavities at lower distances. So there is some kind of like fundamental difference between memorization and learning. And another thing that we tried to do was a kind of like a third type of experiment was, what if now we would take the network that is trained and instead of passing normal samples to it, we will pass adversarial samples, right? So samples that visually are indistinguishable, but are optimized to fool the network and the prediction will fail, right? And this, the response of the network to the normal samples is in blue again, and the response of the network to the adversarial samples is in orange. This is for LeNet on MNIST, this is VGG16 on CFAR10. So what you see again is that you again see this kind of pattern that when you're passing adversarial samples, of course, you're going to get a wrong prediction, but the whole representation of the adversarial samples is very different from the normal representation of your input. And it's characterized by this structuring of this metric space that represents what the network does. So equipped with this kind of, so this was more like the CVPR 2019, right? So there is a fundamental difference between learning and memorizing. There is this shift during training. And what we wanted to know as we started working on started continuing this work, we just wanted to know, okay, is it possible by looking through the topology, not only being able to tell if the network is learning or memorizing, but more specifically to be able to predict the generalization gap of the network? And we did the following thing. We basically did a lot of trainings of many different deep architectures on 3 different vision problems: object recognition, facial action unit recognition, and semantic segmentation. And for each one of these specific trainings, we save 2 things. One is the life and the midlife of the network. So these 2 topological descriptors that I showed you before, there's going to be a number, and the generalization gap of the network. And if you look that, so the difference between performance between test and train. So if you do this, then actually there is a very, very interesting thing. So basically what we found out is that these topological descriptors correlate with the generalization gap. And each of the columns here is a different network. Some of them well-known like ResNet or VGG or AlexNet, and some custom networks here that I denote by conf and 246, where 246 means the number of layers they have. So these networks, they're actually quite different in depth, in number of parameters. ResNet has skip connections, and so on. And each of the points here that you see here, each of the circles that you see here, is a different data set for object recognition. There is CFAR10, and there is CFAR100, and there is SVHN, which is like digit recognition on this Google data set from Google Street Images, and there's ImageNet. And the center of the circle is the mean of the topological descriptor and the generalization gap, and its radius is the variance through a set of trainings that take into account all sorts of different hyperparameters. So we take this network and we train it on, let's say this is CPVR 10, and we vary the learning rate, we vary the amount of data that we are passing, we tried some different regularization and so on. And each time it will have a different generalization gap and the topological and the specific topology. Right? So the life and the inverse of the midlife, they have an inverse correlation with the generalization gap for object recognition. And this is again true for action unit recognition. This is action unit recognition. And this is semantic segmentation. Different networks, different data sets. So then this is a quite a powerful thing. So then we said, all right, if there is this like strong correlation, then maybe we can do something about it. So then maybe I could like tell you a few words about this kind of like different applications that we were like designing in this corpus of work. So the first thing that we tried to do was we designed a small algorithm that would do early stopping based on topology without verification data, right? And the normal early stopping that you would do, you will always have some verification data, some validation data, and you would monitor your performance on that. And based on how this performs, you would stop at a certain point when this plateaus or simply starts decreasing. And what we did is we do not take into consideration any kind of validation set. And we simply look at the way the Betty curve looks like. And when this Betty curve starts shifting from lower to higher distances, we stop. So this was one of the things that we were trying, and you would get something that more or less behaves like this. And as an illustration, you can see here, for example, this was an example that we were showing in the paper as well with VGG 16 and CPVR 10. By looking at topology, you would basically stop here, and the blue and the orange would be the train and test accuracy. But it is not based on the test accuracy. This decision is based on the topology. And the other thing was based on this correlation that we observed between the topological descriptors and the generalization gap. We learned some very simple mapping between the two. And based on this mapping, we make a prediction of how well the network is going to perform on some unseen samples by only looking at the topological descriptors. And if you do this, you can predict the generalization gap with a mean error of 8.4% on object recognition, 5.5 on action unit recognition, and 4.6 on semantic segmentation. Yeah, so these are the main things that I wanted to show you, and maybe as a takeaway and as a kind of like a beginning for questions and discussion, the main important things are that learning to generalize in deep networks is defined by the creation of 2D, 3D, and even 4D cavities in the topological space. And the movement of these cavities from higher to lower distances in the filtration. And memorizing is indicated by a regression of these cavities towards higher distances in the topological space. And the third thing is that life and midlife of these cavities, they correlate with the generalization gap. And given a domain and an architecture, it is possible to estimate this generalization gap without the use of test data. All right, so this was about it.
Thank you for the nice presentation. So maybe I can now start with a question. You showed this curve where you had the train and test set, right? And then you, I think it was towards the end, where you had the training accuracy, the validation, let's say your test set accuracy, and then you stopped at a point based on the topology, and this kind of matched the early stopping.
Yeah, this one, right?
This one, yeah. This is for CFAR 10, but what about like all the other experiments you did, segmentation, like basically for larger data sets, is this also verified?
We did another thing for action unit recognition. So this was the thing that was mainly done for object recognition before doing this more extensive experiments for semantic segmentation and action unit recognition like this year. But what we did there, we have a little paper, which is going to be, I think, in faces and gestures, where we do action unit recognition. So it's kind of the same thing, but for action unit recognition. And you can do that in action unit recognition as well, at least from what we have tried. But I haven't done semantic segmentation or other problems.
Okay. And another question, because you tried different architectures, right? And they all seem to behave in a similar way, right? So that basically these topology descriptors seem to work for different networks like ResNet, VGG, so on and so forth, which is really interesting, right? But is there any network that you tried and by any chance it just didn't work? So these descriptors just don't fit this behavior, or does it work for anything that you tried so far?
So this thing, the thing that you see here, it definitely works like this, but I cannot say if this is really the thing for some other network as well, right? So we tried to kind of like vary this, and this type of pattern seemed quite consistent. This type of correlation that I'm seeing, right? It seems like looks quite consistent, right? And you can, from the amount of networks that we have here, these are quite different networks, right? I could say with a certain degree of confidence that this is quite a robust pattern, and it should make sense that this would apply also to some other kind of different architectures. So you might have more strange things. So for example, we have not tried this at all, like a recurrent architectures, for example. We didn't try this at all, right? And it might apply, it might not. But there is some kind of a strong pattern that we see there, and it more has to do with the way this kind of computational burden is distributed in the network. And you should see this in the topology, that the way this is structured, right? So to answer your question, I think that this is a robust pattern, but I'm not sure to what extent you could like see this everywhere, of course.
Thank you. So I will make one last question. I don't want to hog the questions, but do you think this could be applied to measure the domain gap in the case of domain adaptation?
This is one of the things that everybody asks us. We got this question a lot, and it's one of the things that actually we want to try. Because, you know, yeah, we think that this is very interesting. Totally.
Yeah.
Totally. So, yes.
Yeah, thank you. Okay, we'll let other people ask questions. There are actually some questions also from the YouTube chat. So Christian asked that you argue that topological attributes correlate with the realization gap. Could you elaborate on where you actually see this correlation?
Here, right? So as you make multiple realizations of this architecture, you train it on different kinds of data and across different kinds of network and across different kinds of vision problem, you always get this kind of correlation between life, the inverse of midlife, and the performance gap, be it accuracy, in the case of object recognition, F1 for action unit recognition, and intersection over union in segmentation gap. So
maybe I can elaborate more, because he also wrote that when he looks at the plots of this slide and the next one, he writes, I see 2 to 4 clusters of points for which one could always find a linear correlation. Especially even in the case of 4 clusters, 2 pairs seem to evolve. And then he writes green, yellow as one cluster, blue, red as another cluster. And he argues that this is very weak evidence for a linear correlation, and that it also does not hold along different models. The slope always differs.
True, but this is kind of like a simplification of the visualization, right? So here there are actually many different points along this line, right? And I just try to simplify the way you visualize this in the way that shows basically different types of samplings of this domain, which are different data sets basically here, right? But behind, there are many realization of this with different, as I said, different hyperparameters. It is also true that this slope differs, right? That's why I'm saying that this is given a domain and an architecture. So I'm not saying that you can have this kind of mapping and you can apply this to any network and any kind of problem. Basically, what I'm saying is that you would have to take your network and then you would have to train this network on different types of samplings of this domain, and you will obtain this kind of mapping that I'm showing here. And based on that, you would be able to estimate some generalization gap on unseen data, right? I'm not saying that this is something that is general and universal for all these architectures.
Thank you for the answer. Okay, are there any more questions? So you're welcome to ask questions on Zoom or on the YouTube chat. I'm monitoring that also. So just one more comment from the person who asked the question before in the YouTube chat. He says, well, he thanks you for the explanation. And if you are able to share the plots without the aggregation, are they in the supplementary material, or if you can share them otherwise?
Yeah, this is a good idea, yeah. They're not in the supplementary material, but it makes a good point. So yeah, maybe we should do this.
Okay, thank you. So one last question also from his side. He asked, is there some kind of theoretical hypothesis why a network should evolve cavities when it learns?
Yeah. this is one of the other things that that occurs a lot, right? So, of course, we should have a little bit of set a little bit our boundaries here, right? I mean, all these things that you see, these are some kind of empirical results, right? That show some phenomena, but they are just observations of some particular phenomena. And another step towards a more, let's say, powerful claim would be if you would be able to make some theoretical derivation that would show you that this particular topology, so for example, you can put some bounding on the generalization gap. Can you derive anything like this based on the topology, right? There are results, like famous results in machine learning, right? That do this. Would you be able to do this here as well? And the answer is, I don't know. Maybe that this is the case, but we are definitely not there. We are just making a set of observations of how this topology looks like and how does it correlate with the learning, memorization, and generalization gap, right? So this is one thing. And the second thing that you might ask yourself, why is this the case, right? And this is the thing that I was trying to a little bit explain intuitively in the beginning. And it has to do with the kind of distributed representation that a network that is generalizing should learn, right? So I think that this is the thing that is happening. And it kind of makes sense that when a network learns, its different subparts, they combine in some specific computational patterns, right? There is some evidence, for example, that this is happening in our brain as well. So for example, I've seen papers in neuroscience where they take people, they put them in fMRI, and they perform some task, right? And there is something that is quite similar to this kind of approach as well. So you would get the activation of the different parts of the brain while they're performing some cognitive task. And let's say this task is has a certain type of dynamic. And what you can observe is that when the subject performs that task, there are cavities formed exactly like here in the activations of these different parts of the brain, as you see in fMRI. And then as soon as that cognitive task finishes, that topology collapses. So there is some sort of like structuring of these activation patterns that play a role in the way, in the quality of computational quality of these networks. I don't know if I answered the question in a satisfying way.
I will still monitor the chat. Okay, any further questions?
I have a small question. So basically at the beginning, you explained the way you build your metric space, and then you build your topological space, right? Mm-hmm. So when you build your metric space, every data point can be seen as kind of like the whole set of activations of an image through the network, right?
Mm-hmm.
Kind of. So
every point, there would be like, every point will be a node in the network, right?
Exactly.
Now, you might ask, okay, what does it mean, a point in the network, or like a node in the network, right? Mm-hmm. So you can go, we actually did experiments with different kinds of setups. So in the case of LeNet, let's say, you can actually take every neuron, right? Mm-hmm. In your network. But the problem is that this has a high computational cost. And this depends polynomially on the number of nodes. So you cannot go very far with the number of nodes that we can take into account. So then what we did, basically, we just take the output of a filter in the network, in the cases of convolutional networks.
Okay, so the output of a filter at the single layer.
Yeah, so you're gonna have, I don't know, in the first convolutional layer, you're gonna have, I don't know, 64 filters, right? Let's say each one of them is gonna be a specific operation, one F here, right? And each one of them, when you have an image, is gonna output a tensor, let's say, right? You're gonna have a tensor. And what we do, we take the average value of that tensor, and this is going to be a random variable. And then we compute these correlations between these random variables.
Okay. Okay, so my question was mostly, is the choice of this filter, or like whatever layer you use, relevant? Because my intuition is that people claim in general that in principle early layers in CNNs learn like low-level features, while higher layers learn like more high-level concepts. So my question is wouldn't this be somehow relevant when you're trying to measure like the overfitting patterns of your network? So is it maybe harder to overfit, like to detect overfitting in maybe like early layers versus later layers? Like, did you do an experiment regarding that?
We tried many different things actually, and in some particular networks, as I have told you, you can have a very high number of nodes. This is very true for networks that are quite deep, right? So let me tell you a few things that we have noticed. So one of the things that you can do to keep your number of nodes to not boost your number of nodes too much is, for example, to randomly sample them. So let's say you have a network with like n nodes, you'll have n filters all across that network, and you randomly sample half of them, right? And you compute the topology and you do exactly the whole things, but it's a random samplings of those nodes. In that particular case, this is very consistent. So even if you do a random sampling of the nodes, you still observe this pattern. This is what we have seen. So this is like one thing. The second thing is that this also holds per layers. So if you would, let's say you have 30 layers in your network, right? And now instead of randomly sampling across the whole network, you choose a particular subset of layers. Let's say, the first half of your network, or the second half, or whatever you want. And this still holds.
Okay.
So what I'm trying to say, what this means basically is that this type of structuring that you observe as you train your network is global, but holds in even if you would limit yourself to a more local view as well.
Okay, that's interesting.
But I'm not saying that it might be actually very interesting, and this is another thing that sometimes like people ask, and we are very interested to explore is basically when what you are like asking is that in a DIMNet you have this function, right? And when I'm saying function, I'm referring to these activations to input, right? So this is one thing. The second thing is you have structure, right? These nodes, they're going to be in particular positions in the network, and they're going to be connected in particular ways, right? So one question that you might ask yourself is, what is the relationship between structure and function? And this kind of goes back to this question is that, okay, at different parts of the network, I'm going to have different structure because I'm now at the beginning or I'm in the later part. And does the function differ? Or if I'm adding skip connections, what's happening? If I'm putting some other kind of structure, what's happening, and so on and so on, right? So this relationship is, I find, very interesting, and it's definitely worth exploring more.
I see. I mean, but since, I mean, from the first part of your answer, though, you were kind of saying that from your findings, kind of like these kind of topological insights that you reach are somehow persistent across different parts of the structure, right? Of these networks. Okay.
So
okay, no.
If you take the second half or the first half or some subset of layers, let's say, as long this is representative, and I cannot give you actually some feeling of what does this mean, but this sampling has to be representative. So if you take, for example, half of the nodes randomly, it will hold. But if you take 5% of the nodes randomly, maybe not, right? So you need some kind of representative sampling of the nodes in your network, and this will be some kind of simplified representation of the whole network, let's say, right?
Okay. Okay. Yeah, interesting. Thank you.
Okay, thank you finally for this nice talk. Unfortunately, we're running out of time, but thank you especially for the discussion and for all the questions on YouTube. So the video will be available later on. So also, if you want to watch it, if you want to share the link, please go ahead. And thank you again for such a nice presentation, Ciprian.